Okay, so today I'm going to work through this week's lesson, which is correlation and simple linear regression. So we have at the beginning here, we do have this line about adding this package called lterdate. We're pretty sure this is outdated, and lterdate is now a part of the tidyverse, so you can kind of ignore this. But to start off the lesson, I'm going to open my ESS 523AR project. Remind me later. Okay, and then I do want to double check to make sure I have all the packages needed today, which are most importantly the two that we added last week. So double check in case you didn't add the ones from last week, which were lterdatasampler and our statics. I have not added them yet to the setup script, so I'm going to do that now. lterdatasampler and our statics. Let me double check that spelling. Yep. Okay, and then save that setup script. And then we're going to create a new markdown file to demo today. Call this correlation and simple linear regression demo. Oops. And the first thing we do always is run that setup script. Ah, yes. What was that? Oh, can you put the... Yes. Okay, so first we're going to work through how to run a correlation test in R. We are going to do this with the same and vertebrates data set that we used last week. And we use a correlation test when we have two continuous variables that we want to test if there's a relationship between the two and how strong that relationship is. So to start off, let's say we wanted to test if for our salamanders, if the length variable is correlated to the weight variable. So essentially we want to see if our hypothesis might be the longer the salamanders are, the more they may weigh. And we can test if that relationship exists with the correlation test. So first, I'm going to load in the data and filter it to just salamanders. This is the and vertebrates. We'll run that. And then filter to salamanders. And this is using a new function, a new suite of functions we haven't used yet, from the stringer package, which comes with the tidyverse. Here we're going to use this function called stringer detect. This will do string matching. So essentially, we know that in our and vertebrates data set, we have two salamanders, because we worked with this yesterday. But say you had a bunch of trout and a bunch of salamander, and you wanted just the salamander species. Also, I don't want to worry about typing out the full Cascade Torrent salamander, and then the giant salamander is the other one, because then spelling issues might come into play, etc. So this function, str_detect, first you give it the column name you want to filter on. In this case, it's species. And then you give it a string that you know exists in all of the rows that you want to return. In this case, we know that both of our salamander species names have salamander at the end. So we can just give it salamander. So I want to take, and I'm going to save this as a new variable called sal for salamanders. Cannot spell this morning. And then we do filter And then first, instead of giving it the column name first, we do str detect and another nested parentheses, and then we give it the column name we want to filter on. So species, and then in quotes, since it's a character string, salamander. And we'll see when we run this that now we have this data set called sal, and it has a lot less observations because we filter out just the salamanders. And you can always check with that. There's a lot of ways we can do this, but the base R way is that unique function. If I do unique sal $ species, just to double check that I have just the 2 salamander species returned, we see in this sal data set we have the coastal giant salamander and the Cascade torrent salamander. So that was just a check there. But then we want to add one more thing. We want to drop all of the NA observations. And so we're going to use this drop NA function, and we give it all the columns. We want it to search for NAs for that variable and remove that row if it has NA. So drop NA, and we're going to be doing this with the length 2 millimeter. You could do the 1 millimeter length if you want. And weight. Okay, so I'm going to run that again because I want to refresh my sal data set. And now we'll see that did something because now we have a lot less observations. So it removed all those NA values that we want to get rid of. Okay, so as was one of the first lessons we did in this class, exploratory data analysis, let's do that first here. Let's just first visualize this relationship between our salamander length and weight. So I'm going to do ggplot with our new data set. I'm going to do geom point, since these are 2 continuous variables. And let's put length on the x-axis and weight on the y. Run that. I'll zoom in here. And so it looks like there is pretty strong relationship between length and weight. So with correlation tests, and then what we also see here, this chart is showing us a positive relationship, that as length gets larger, as does weight in these salamanders. So now we see this visually, but we want to statistically test if this relationship is statistically significant or not. So we can check for, so with correlation tests, our 2 assumptions on if we were to use the parametric test, the assumptions are that our 2 variables have a linear relationship and they both have a normal distribution. And so actually that first assumption, linear relationship, does not look met here. This is more of a curve, almost a logistic relationship is what we're seeing visually. But then this second assumption is that they both follow a normal distribution. So we can look at this visually with our histograms. Do hist length, do hist weight. Okay, so this looks quite skewed for our weight variable. If we look at the length variable, a little less, but still pretty skewed to the right here. But we can also statistically test for normal distribution. And we did want to show, so in the data sets, we were working in this data set last class, we talked about since the sample size is huge, we can kind of, the normal distribution test is kind of moot. But we did want to show this new function, slice sample. So say we do still want to statistically test for normal distribution in this data. We can use this function slice sample to pull out a random subset of the data. And since we know the Shapiro test won't run on anything over 5,000, let's pull out a random subset of 5,000 so we can still run that Shapiro test. And we have this written in the lesson plan, how we would do this with the base R Shapiro.test. But now that we have the R statics package, we can actually do this a little simpler with tidyverse format. So let's take our SAL data set, and then we want to slice sample. And then the argument we give it is n, which is how many random rows you want to pull. We're going to do 5,000. And then we can pipe that into Shapiro underscore test, which is the R statics version. Shapiro dot test is the base R version. This is easier because then we can actually just pipe the output directly into Shapiro underscore test. And then we can do this for each of our variables. So let's do it with length since that was really skewed. When we run that, we get the output of the Shapiro test, and we have a really, really small p-value, e to the negative 42. So this is telling us that since the null hypothesis is that your data is normally distributed, this is telling us our data is definitely not normally distributed. And so in this example, instead of going through and transforming variables, we're going to choose to just use the non-parametric correlation test. With correlation test, that is the Spearman test. If we were to try and log transform our variables and use the parametric test, that would be a Pearson correlation test. And we'll show you how you can specify that with the core test function. I'm going to close out of this. Okay, so let's do our correlation test. So the function is core underscore test. First, we give it the data set, which is SAL. And then we specify the two variables we want to perform a correlation test for. And again, we put these within this small lowercase c concatenate function. Vars equals, and again, spelling is important, but we don't need to put the variables in quotes here since we're using tidyverse syntax. Length 2 millimeters and weight underscore grams. And then we specify the method. So this is where we can say either Spearman or Pearson. Since we want to use the non-parametric, we're not going to deal with transforming our data or anything. We're going to specify Spearman. And then I've missed one other argument, which is alternative equals 2.sided. I think this might be what it does by default anyways, but we're specifying this because we want to test both for positive and negative correlations. We want to test in both directions. Okay, spelling. Okay, so now we run this. We perform our correlation test, and we get this single row of data returned. The two main things we want to look at is first the p-value, this lowercase p. Here it just shows 0 because often once it gets to a certain, amount of decimal points, it'll just round up to 0. So this tells us that the p-value is very, very, very small, much smaller than 0.05. So this is telling us that our relationship between these two variables is statistically significant. And then second, we look at this correlation statistic, which is talked about in the lesson plan, but this correlation statistic ranges from -1 to 1, where 1 would mean there's almost a perfect positive correlation. -1 would mean there's a perfect negative correlation. And 0 would mean no correlation whatsoever. So our statistic is 0.98. That's almost a perfect positive correlation. So here we found out that salamander length is significantly positively correlated with its weight. So the longer the salamander, the more it weighs, which when we think about biologically, that makes a lot of sense. So that's correlation tests in R. However, the limitations with this is that you're just testing for if the relationship exists and in what direction. Is it a positive or negative relationship? So next we're going to get into performing simple linear regression, which goes a bit further than these correlation tests to define this relationship, and then we can also create a model so that we can predict variables given our line of best fit. So we're going to use this, we're going to perform a simple linear regression with a new data set, and this is another data set that comes with that lterdatasampler R package. There's a whole suite of data we'll be using from that package for these next few lessons. But this crabs data set, we have a lot of details here, but essentially they collected size characteristics of crabs all along the East Coast from Florida to Massachusetts. And so this data set actually gives us a perfect opportunity to test Bergmann's rule, which is the theory that species are larger at colder temperatures. And so we can test this here because we're assuming that from Florida to Massachusetts is a strong enough climatic gradient that it's much colder in Massachusetts than it is in Florida, which we know. And so since we know there's this gradient in temperature from warmer to colder, we can test, do the crab sizes get significantly larger the colder it gets? So that's testing Bergmann's rule. And now a simple linear regression, as opposed to correlation where it didn't really matter, what variable was X or Y, we're just testing a relationship among two variables. With linear regression, we have a defined X and Y variable. And our X variable is, you might hear X and Y referred to as a lot of different pairs. Cause and effect is one, so X is the variable that is changing, that's causing the change, and then Y is the effect, is the outcome of that change. You might hear the explanatory variable and the response variable, the predictor, the outcome. So X, in our case, is the latitude. That is what is changing. And then our Y, our response variable, is the crab weight, because we want to test if the weight is changing based on what the latitude is, which is a proxy for temperature. So this data set is called Pi Crab. Let's do simple linear regression now. Oops. Data Pi Crab. Oops, lowercase. It autofilled for me. Okay, so when we load Pi Crab and we look at this, we see that we have a date, the latitude, and then what we are interested in is the size, which I'm guessing is, I think it's the carapace size. But I'm going to use my help tab to search this data set to double check on that metadata. Yes, so size is, so each row is an observation of a single crab, and we have the date, the latitude, the site it was collected at, and then size is the carapace width of the crab in millimeters. Okay, I'm going to jump down to visualizing this relationship. We have a little note here. So a simple linear regression, we do not have the assumption, we don't need to meet the assumption that our variables are normally distributed. However, with linear regression, our assumption we try and meet is that the error of the data is normally distributed. And we'll get into more of that in next week's lesson, so we can kind of put in the back of our minds for now. But first things first, let's visualize what this relationship looks like. And so a note here that now when we're visualizing this and setting our x and our y, it does matter which variable is our x, which is our y. So in this case, again, x is our explanatory variable, which is latitude in this case. And then y is the response variable, which is the crab size. So let's make another chart like last time. We don't need to do any cleaning of the data ahead of time, so we'll use PyCrab. Point. So x is latitude, and y is size. But I'm going to add one more thing that is new for us, which is this function called geom_smooth. And this will add a line of best fit to our chart. And so we specify our method, which is LM, which stands for linear model, which is what we use for linear regression. And then we're going to set SE, stands for standard error, to false. I can show you what, if we set that to true, oh, I did something wrong. Hang tight, folks.
Interesting.
Right? That shouldn't matter, but maybe it does. Ah, it did. Okay, so this is an example of when it actually does matter where you put your aesthetics. And so I think it is because we were computing, it was actually, geom_smooth does statistics in the background. And so since we didn't put our x and y in the data part with ggplot, I think it didn't know how to do the model.
Yeah, I remember when you want to apply multiple geoms to a single data set, it needs to either be in ggplot, the top line, or explicitly identified in all of the other ones below it, right? So it would be using the same data set, would be my guess.
So what this did was it added this line of best fit. And then just to show you what, if we add that standard error bar, it adds the, which is kind of hard to see, but it also adds the standard error lines to the line of best fit. Okay, so we're looking at this visually. We do see there's kind of chunks here because there are, instead of a super continuous line of latitude, each site had a single latitude where multiple crabs were collected. So that's what we're seeing here with these kind of grouped observations here. But we do still see a continuous line of latitude from south to north. And our crab size, which generally looks like, as we go further north, get a little colder, the crab size appears to be getting visually larger. But let's statistically test for that. So what we have here that we've added to our chart is our line of best fit. So if you remember from stats, y equals mx plus b, that's what we're working with here, where y is our response variable, which is the crab size. M, or what we refer to as beta 1, is the slope of the line multiplied by our x variable, which in our case is latitude, plus the constant, or the y-intercept. In this case, we refer to as beta 0. And then we also add in this error term, which is e. That was crazy.
It's really good today.
And so that is what is being developed when we run the linear regression in R. And then we can actually use that line of best fit to predict other crab sizes based on other values of latitude. So we'll get to that in a second, but let's now execute our linear regression. We're going to use this function that's lowercase lm, which stands for linear model. And this comes with base R. Since R was developed originally as a statistical programming language, it has a lot of great base R stats. So we're going to just stick with lm. And we also want to save our linear model to an object, as opposed to the other statistical tests that we've done where it'll just directly print out, our p-value, our statistic. Linear models have multiple types of metadata with them, so we want to save it as an object, and then we have to call out our specific, we want to know the p-value, the statistics, etc. We use this function summary. And so I'm going to call this, I'm just going to call it model. We do lm, and then we type this out as what's called a formula. And the formula format is y tilde x. So you can read this as, I want to test for how size, I read the tilde as, varies by latitude. So you can think of that when you think of formula. I want to test for how size varies by latitude, because the order of this is important. It's always y and then x. So size, latitude, and then our data, we specify our data, which is pi crab. And then I want to do summary, I want to return summary of model. So we run that. We've created this model object that's actually, we can see it's a list of 12. It has a lot of metadata with it, but when we use summary, it gives us just the stuff we want. And so we have a little more information here than other statistical tests, but a few things we want to look at first. When thinking about that y equals mx plus b, we have, let me close out of this. This value here, negative 3.6, this estimate for intercept, that's our intercept value. And since it's negative, we do minus 3.6 instead of plus b. And then our slope of the line is the estimate for our y variable, which is 0.49. So statistically, this is telling us that for every 1 degree increase in latitude, we have about a 0.49 increase in carapace length, which we know is in millimeters. But the first thing we want to look at is this model statistically significant? And we do that by looking at this PR column, standing for probability, and then we want to look at the row for our y variable, not the intercept. And so we see, we have very significant e to the negative 16th value, much smaller than 0.05, which means this is a very statistically significant model. So now that we have our model created, we can now use that model to predict other values of crab size. So let's say we wanted to predict, say we didn't get to sample sites all across the East Coast, but we now have this statistically significant model we can use to predict what crab carapace size would be at other latitudes. So to do this, there's a few things we need to make sure we are specifying correctly in order to use this predict function later. So what we're doing here is creating, let's just say we had 3 other sites that we knew their latitudes were 32, 36, and 38. We didn't test these yet in the data set. Predict sizes. So I'm going to create a new data frame. I'm going to call it new lat. And I create a new data frame with the tibble function. Since we're sticking with tidyverse syntax, we use tibble to create a tidyverse data frame. It's tibble. And we're going to predict pretty much this is just a 1-column data frame, but the column name needs to be the same name as our y variable in our original data. That's important. And I'm going to give it our 3 new latitudes, which was, what did I say, 32, 36, 38. 38. And then I can use the predict function. And predict first takes your model you just created. In my demo, I called it model, but in the lesson we call it SLR model. And then this argument new data, which is our new latitude. So I want to predict I called it model. And then new data is new lat. Okay, so now when we run this, it returns the predicted x, which in our case, or the predicted y, which in our case is the crab size, for each of those new latitudes, and it returns it in order. So this is telling us at a latitude of 32 degrees, our model predicts that crab carapace width would be 11.9 millimeters, and it does the same for 36 degrees latitude and 38 degrees latitude. Okay, so that is your brief overview of correlation and simple linear regression. Next week, we'll get into multiple linear regression when we have more than one predictor variable. But for your assignment, it's a little different than other assignments. We're using an entirely new data set. There's actually 2 data sets because we're going to make you use a join in the assignment. But we did want to kind of give an overview to set you up for this assignment. So really, what we're doing in the beginning of this exercises section is loading and cleaning the data for you. But so you could just run this and, use it as is. But we wanted to inform you of some of the stuff that is going on in here because it's a little confusing because we're using water year. So for this assignment, I'll just do a little demo here, using 2 new data sets that also come from the LTER data sampler package. So we can just copy and paste this without loading any new packages. So it's going to load 2 different data sets. And these are an air temp data set and an ice cover data set. And this is data from, it goes all the way back to like the 1870s. It's annual data collected at 2 lakes in Wisconsin that are near each other. And each year it collects air temperature and ice cover. So we're going to use this data set to test for the relationship between air temperature and ice duration, with the idea that if the temperature gets warmer, the ice duration over winter would be shorter. It's melting faster. And so the first step here is we give you the code to clean these 2 data sets in order to allow you to, what you're asked to do in the first question, join them together, because right now they're separate data sets. So we need to clean these by first getting them both standardized on the same year. Essentially, what we want to do is have, for each data set, for each year, we want the average temp and the average ice duration. But since we're working with water, we do this by water year, which is not January to December. Water year is October to December.
To September.
Yes, September, sorry. October to September. So I think of these as like fiscal years. Like they don't really add up. You start in one year and you end in the future year. That's what water year is like. And so for ice cover data, if we look at it, let's see. For each year, there's 2 lakes in here. but we have the date that the ice was on the lake and the date the ice was off, and then they use that to calculate ice duration, which is number of days of ice. However, in this raw data set, they're pulling year from the ice on year, but when working with water years, like fiscal year, it's the future year. So that's why we're doing year plus 1, because that would be that ice year's water year. And then we calculate the mean ice duration. And then second, we clean our air temp data. And we do the same thing here, but the air temp is calculated daily, maybe even monthly. Yes, we actually have daily air temp data since 1870, which is crazy. So what we need to do first is we want to, for each row, calculate that air temp's water year it's assigned to. And so this is where that lubridate package comes in, is we're creating this new variable water year. If that date's month is less than 10, so it's 10, 11, 12, then we give it the current year. Otherwise, we give it the next year. Is that right? We're doing that right? Yes. Again, fiscal year hurts my brain. So essentially, we're just creating this new variable water year, and it's calculating that date's water year based on what month it was. Because again, October through the following September would be, like for example, starting next month, October, we will be in water year 2026. So thinking like that, that's what we're doing for every date here based on its month. And then once we have our water year, we can then group by water year to get average air temp. And all of this is to say we're just standardizing the two, so we have, because this is calculated, the dates don't line up, so we want to standardize both of them. So we have one average value of ice duration, one average value of air temp for each year, and we are identifying as water year instead of calendar year. But we have all this code for you. You can just copy and paste it and then do the assignment, but we just want to explain what is going on here in the data cleaning. Okay, and that is this week's lesson.